Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving here today, as it is every day here in my virtual classroom. Congratulations on making it this far in the Big Ideas Math Integrated Math 3 textbook. We are on the Chapter 4 test and cumulative assessment. Now, as all things with this set, first of all, in the description section down below, you can download the PDFs of each of the parts individually. You can also find the timestamps of each individual problem from the chapter test, and then from the cumulative assessment, we'll break it up into those two parts. Maybe you're just assigned to one, maybe you're just checking out one set. Most people probably check out the test portion, but who knows what you're doing with what. That being said, these problems can be a little bit harder here and there. Even the review questions were a little bit harder, but it's at this stage that I assume that we kind of know what we're doing. So I want to get through the problems as quickly as possible as well, or efficiently. Every so often, if there's something really tricky, I might even struggle through it, but I also want to maybe teach those little parts if it's like a brand new or very foreign thing that we haven't seen very often, especially if it wasn't in the review. Otherwise, we're going straight through the problems kind of as best as I'm able to with what I can write, what I can calculate. Get your graphing calculators ready. I'm going to attach graph paper as needed for whatever's here. Problems in the test portion are randomized order, like we might start out of section 4-6, who knows. They're not just straight in order, so just keep that in mind. Okay, without further ado, we're going to go ahead and get into them. So, let me get my pen ready, because I was not ready there. Let's go to number 1. Solve the inequality 5 times the square root of x minus 3 minus 2 is less than or equal to 13, and the equation 5 times the square root of x minus 3 minus 2 equals 13. Describe the similarities and differences. I don't like describing similarities and differences. If you don't mind, I'm going to do the equals one first. I think that that's more in tune with what we practice, and then the inequality one will follow suit quite a bit. I'm going to isolate the radical by adding 2 to both sides, then dividing both sides by 5, and then we square both sides. So x minus 3 equals 9, and then x equals 12 when you go ahead and add excuse me, the 3 over. I'm going to double check I even did the numbers right with there. I want to make sure that I do get the 12 the same way. I'm not going to check for extraneous solutions. This should work just fine. There was a positive on that side. We're good there. Let's do the inequality version. We get the same setup, but this is greater or less than or equal to 13. Now, same rules apply. We need to get this thing balanced. We add 2 to both sides, divide both sides by 5, and square both sides. We get x minus 3 is less than or equal to 9. Add 3 over x is less than or equal to 12. Now, there's more I need to state on this one, though. Like I said, 12 does work properly for here. This also has a domain concern. This x minus 3 inside the square root must also be greater than or equal to 0. So x has to be greater than or equal to 3 as well. Less than or equal to 12 to satisfy the inequality, greater than or equal to 3 to be a real number set. So x needs to be between 3 and 12 to satisfy the set. Excuse me. All right, describe similarities and differences. When it comes to process is very similar. The process for isolating x is equivalent for both equations and inequalities. Now, sometimes you need to flip an inequality over if you divide by a negative or something like that, but the process is the things you got to do. Add 2, divide by 5, square both sides, things like that. They both share a solution of x equals 12, and both of them would have to test for extraneous solutions in some cases, though not in this case. We need to check for domain concerns because there is an infinite number of solutions. Infinite number of solutions, geez. For the inequality, we need to restrict its lower end by its domain based on the square root. So there are a lot of differences as well, and I'm trying to type all of them out when we're referring to it. So yeah, that 3, x has to equal 12, but it has to be greater than or equal to 3. Well, duh, 12 is greater than or equal to 3. But here, less than or equal to 12 means it'll keep going forever, even to negative land, so we have to stop it on that, on the inequality. All right, I'm going to move forward. Number 2. Describe the transformation of f represented by g, then write a rule for g. Now, f of x equals the square root of x would have been the initial. I'm going to copy and paste this thing over. It might look a little bit blurry, but I think we can see everything we're going to need to see on here. Looks fine. Okay. So for this one, square root of x has, like this would have been the basic graph here. Over 1 up 1 over 4 up 2. It looks like it just translates 3 units to the right like that. So that's exactly how I'm going to describe it. The graph of g is a translation 3 units right of f. Now, as far as that equation goes, it's just going to be an x minus 3 that's inside of the function. The first time I'll write it will be like f of x minus 3, like that. That's how the translation to the right goes. So g of x will equal the square root of x minus 3. There's nothing else that's going on, no stretches, no reflections, only horizontal translation. Number 3, we have cube root of x. Let's copy and paste that guy. So this one has at least 2 changes that I can see. Do you see what I see? And you could describe this first one in one of 2 ways. You can either describe it as because the original parent function would have gone 1, 1, and 8, 2, like this. It would have gone a little farther out. Don't really worry about that, but it's a curve this way. So you can tell it flipped over. Now, did it flip over by means of rotating, not rotation, but if it rotates over, I guess I can't rotate it. Does it flip left and right, or does it flip up and down? Either way, it goes that direction. So you can either flip over the y-axis or the x-axis. Doesn't matter which one there. I'm going to say the x-axis. I prefer flipping vertically. So the graph of g is a reflection in the x-axis, followed by a vertical stretch. You might notice that instead of going 1, 1, it's going 1, 2. A vertical stretch by a factor of 2 from f. So here, there are 2 things going on. We are affecting, in this case, f of x by multiplying by -2, the vertical stretch and the flip. So it's going to be -2 times the cube root of x. Instead of 1, 1, it's 1, 2, and it goes negative like that. And there's the equation. Number 4. F of x equals 5th root of x. Now, 5th root of x is like cube root of x in every which way that we actually care about for this problem, including the stretch, because we're only showing what happens when it goes up by 1. So the only difference in our answer is we're going to have a 5 there instead of a 3. Otherwise, the idea of center, translation, all that kind of stuff's the same. Even end behavior, as far as all real number domain and stuff, all looks the exact same. So what do you see? The center would normally start at the origin and it's translated 2 units up. And from 2, it goes over 1 up 2, which means it's doubled. So the graph of g, we're going to talk about the stretch first. G is a vertical stretch by a factor of 2 from f, followed by a translation 2 units up. So our g of x, our g of x is going to double the f of x, and it's going to add 2 on the outside of the y. So both things are affecting y. So g of x will equal 2 times the 5th root of x plus 2. You go over 1, you go up 1 to the 5th root of 1, which is still 1, but doubled is 2 like that. Okay. All right. There are some things with graphs, sort of. We explained graphs. I don't know if we graph for ourselves. Numbers 5 through 8, we're going to simplify these numbers. Oh, some variable ones. It says explain your reasoning. I'm not big on explanations for these things, except for things that I state out loud. Apologies on that. I'm going to go ahead and get started, though. So my explanation is we can convert this to the cube root of 64 and square it. And cube root of 64 is 4. 4 squared is 16. That's my explanation for simplification on number 5. Number 6, we have negative 27 to the 5/3 power. Given that both the 5 and the 3 are odd numbers, not only is this allowed to be, applied, but our final answer should also be negative. So this is the same as the cube root of negative 27 to the 5th power. Cube root of negative 27 is negative 3, and negative 3 to the 5th power is negative 243. All totally valid, and the only answer that gets applied there. Number 7. Number 7, it never said assume all variables are positive, so keep that in mind in case we have to do something with this to get absolute values with variables. We have 4th root of 48 times x times y to the 11th times z cubed, and that is an 11 there. I want to be careful because I wrote a 4 on the other part where it's 4th root. Okay, the 4th root of 48 will be something we got to break down. 48 itself is not a perfect 4th value problem. 4th root of x, that's going to stay inside that 4th root. There's nothing I can do with it. In fact, same with the z. The only one I can do something with is the y, and we'll get there in a moment. That almost looks like a 4 again. Hopefully you can see that it's not. I'm going to try that. That now looks like a 14. So let's turn it into an 11. Okay, the two things we can tool with are this guy and this guy. So let's take a look. The 4th root of 48, 16 is a perfect 4th power value, so 16 and 3. And the 4th root of 16 is 2, so that's 2 times the 4th root of 3. As far as y here, this is y to the 11 over 4 power, which means we divide 11 by 4. 4 goes into 11 twice with the remainder of 3. So it's y squared with the remainder of 3 that would go inside there. So some things stay inside the 4th root, some things come out. The only things that come out are a 2 and a y squared. We don't need to take absolute value because squaring a negative number will still turn positive. Inside of the 4th root will be everything else. The x can never come out. The y cubed, the remainder, stays inside there. And the z cubed, which always was there, stays inside there. Oh, I'm missing the number portion. Give me 1 second. Let me ungroup that. I'm missing the 3. No. I'm missing the 3 that goes with this guy right here. There we go. That's it. So 2 times the 4th root of 3 is root 48. All right, number 8 is cube root of 256 over cube root of 32. Now, I'm curious as to whether 32 can divide by 56. It can. So I think the fastest way to do this problem is to literally do that division. There are other ways of going about it. I don't imagine I want to work those ones out if it's there. Remember, this is the same thing as cube root of 256 over 32 like that. And if they divide, they do. You get 8, which is nice. So cube root of 8 is a great simplification. But you can take the cube root of 8, and that's 2. And you're done. Another way would be trying to do something to rationalize the denominator. But if you can make it be like this, so you don't apologize and you do it. Sorry. Okay, number 9. Write two functions whose graphs are translations of the graph y equals square root of x. Is this open-ended? The first function should have a domain of x is greater than or equal to 4. So let's start with this one. So part A, domain, x is greater than or equal to 4. Second should have a range of y is greater than or equal to negative 2. To be greater than or equal to 4, we need to make sure that we shift this at least 4 units to the right. Or sorry, not at least. It's got to go 4 units to the right. So y equals, so we can do square root of x minus 4 like that. Now, this can be the final answer. We could add whatever k value you want. You could do minus 1. You could do nothing, right? You could leave it like that and it's good. This graph goes to the right. There's your domain. Second one, the range needs to be y is greater than or equal to negative 2, which means the graph still goes upward, but now this graph needs to shift downward. So we can say square root of x and then minus 2. If it shifts downward, it goes up from there. We're good to go. Inside of here, you can do x plus or minus whatever you want. I'm going most basic version. Choose to do what you like on that. It's a little open-ended, but we have to make sure we satisfy those parts of the domain and range. Okay, number 10. In bowling, a handicap is a change in score to adjust for differences in the abilities of players. You belong to a bowling league in which your handicap H is determined. I don't need a handicap. It's determined using the formula H. Actually, there are probably a lot better bowlers. I'm not a good bowler. I was just thinking I don't need bumpers, but I realized that I'm going to score like a 140 at best. 0.9 times 200 minus A, where A is your average score. Find the inverse of the model, then find the average score for a bowler whose handicap is 36. So I'm going to try and get A by itself. I'm going to divide both sides by 0.9. So H over 0.9. I kind of don't want to use the decimal there, but it's whatever. Equals 200 minus A. I can add A to both sides and subtract H over 0.9 to both sides, and you will get A equals 200 minus H over 0.9. Now, that's an answer for the inverse. 0.9 is also 9/10. So when you divide by 0.9, you multiply by 10 ninths. So just keep that in mind that you could also write this as 200 minus 10 ninths, 10 ninths h. So I don't know which one you prefer with that, either or. It says handicap is 36. That's kind of why I like the 10 ninths more. I think it's an easier division for me. Actually, both are fine. So A equals 200 minus 10 ninths times 36. 36 over 9 is 4 times 10 is 40. So 200 minus 40 is 160. Oh, good. I needed that handicap if I average 140 or something like that. Oh, sorry. My average is 140. So if their handicap is 36, their average must be 160 to begin with, right? That's kind of what they're saying for that. Well, that's exactly what they're saying for that. Okay, number 11. So you can see these questions are very scattered. They are not going necessarily in progressive order from section to section. So go with the flow, guys. It's the whole chapter. All in radicals, rational exponents. The basal metabolic rate of an animal is a measure of the amount of calories burned at rest for basic functioning. Ooh, humans on there. Let's see if that's a good or bad number. Kleber's law states that an animal's basal metabolic rate R in kilocalories per day can be modeled by R equals 73.3 times W to the 3/4 power, where W is the mass in kilograms of the animal. Find the basal metabolic rates of each animal in the table. Okay, this is one where I'm going to go to the graphing I'm going to go to the calculator as a general thing. It's just going to be easier to work off of here. Now, if you can't see these numbers, I'm going to go ahead and pop them up, copy and paste them. They'll still be a little blurry, but there they are. We're going to substitute these values in for W. Now, excuse me. Sorry for clearing my throat in the microphone. I do not intend on doing that. I do need to sip water here in a second. I'm going to write that equation in there. Let's go to... This is going to have to be an X instead of a W, and use parentheses around this. So I can either go to the table, or we also found that you can go to variables, vars, y-vars, and function, and in your equation you can type in these different numbers if you'd like to. This is probably the slower route than using a table and hitting ask, things to ask for, but here's for a rabbit, a sheep, and this is just, there's nothing else to do in this problem, guys. It's straight substitution. You're substituting these values in for W to find R, because these are the weights and mass, right? I want to make sure. Mass in kilograms, W is the mass, find the basal of each animal. Okay, yes. So we're just substituting these ones in. That's the sheep. The human is 70. And again, I don't know if these numbers are good or bad things for humans compared to that of, say, a lion. And a lion. A lion. So I'm going to type in those numbers. Or write in those numbers. Rabbit. Sheep. Sorry, you can't see this. I'm letting you look at the numbers there so you can maybe write them down. Human and lion. So for rabbit, I'm going to write their basal rate. What is this? Kilocalories per day. So 100, I'm going to round to the nearest number. 146 kcal day. Sheep, about 1378. Human, I guess the higher, the more that you burn, huh? 1774. I put 1773. All right, now you can look at this screen. And the other is 4044. 4044. And lion 4044. Okay. Are approximately equals. Because those are rounded values. Okay, number 12. Let f of x equal 6x to the 3/5 power. And g of x equal negative x to the 3/5 power. Find f plus g of x and f minus g of x. Now, these are like terms, so this will be just fine. When you do f plus g of x, that's f of x plus g of x. We have 6x to the 3/5 plus negative or minus 1x to the 3/5, which that simplifies to 5x to the 3/5 power. I'm fine leaving it like that. State the domain of each. This domain should be all real numbers. There's no issue with taking odd roots. Remember, that's a fifth root. There's no problem with taking odd roots of negative numbers, and that's exactly what we'd be dealing with. They say find f plus g of 32, so let's get that. F plus g of 32 is 5 times 32 to the 3/5. Now, before you jump to the calculator, that does mean 5 times the 5th root of 32 cubed, and the 5th root of 32 is 2. So that's 5 times 2 cubed, or 5 times 8, which is 40. So f plus g of 32 is 40. It's within the domain that is all real numbers. Now, f minus g of x, we're going to do all the exact same things. What am I writing? F minus g of x is going to be f of x minus g of x. So we're subtracting the negative, which is addition. And that'll become 7x to the 3/5. And all the same stuff will be there. So when we do f minus g of 32, by the way, domain's all real numbers. Here's box, domain is all real numbers. When we do f minus g of 32, no change in the 3/5 power and stuff, guys. Now we just got to do 7 times 8 instead of 5 times 8, and this will be 56. So I'm not, I'm going to cut corners on that question when it comes to the final thing you got to do. That's still going to be an 8 there when all said and done because it's the same 32 we used from before. Number 13, let f of x equals 1/2. So it's the same stuff, only now we're going to do, it looks like, multiplication and division. So number 13, let f of x equal 1/2 times x to the 3/4 power. Let g of x equal 8x. That one's linear. They say find f of x, f times g of x and f divided by g of x and state the domain of each, yada yada. This time we're going to talk about domains a little bit differently here. F times g of x will be 1/2 x to the 3/4 times 8x. That means we get to do 8 times 1/2 and x to the 3/4 times x. Now that's x to the 3/4 times x to the first, or x to the 3/4 plus 1, or x to the 3/4 plus 4/4, which is 4 times x to the 7/4 power. That's one version of what you can write. Now keep in mind, we can also rewrite this as 4, well, there are a couple things we can do. 4 goes into 7 once with a remainder. I guess we can leave the 3/4 like that, right? We can leave it like that if we wanted to, but I want the radical version. Now, because there's an even root, our x's need to be positive, or excuse me, non-negative, greater than or equal to 0. So that's your domain. So either or can be written there as we do f times g of 16. F times g of 16. And I'm going to put it in this one because I can do more with that personally. That's 4 times 16 times the 4th root of 16 and then cubed. 4 times 16 is 64. 4th root of 16 is 2. 2 cubed is 8. 64 times 8 is, I don't know, 512. So f times g of 16 equals 512. 16 is greater than or equal to 0. That was fine to substitute in. Now we'll do f divided by g of x, which is going to be 1/2 x to the 3/4 divided by 8x. And I know that looks weird. That means the 2 can go down with the 8. When it says 1/2, it's divided by 2, and also then divided by 8. So that's really 1 over 16. So it's x to the 3/4 over 16x. Now, as far as I think rational denominators go, I think this is good. Like, it has a rationalized denominator, and that number on top is less than 1. So I think this is an appropriate final answer, as in radical form it would look like this. And I think that that is just as best as you can get with those. Now, the domain's the same when it comes to the 4th root portion right here, but now this linear function is going to have an issue when it comes to dividing by 0. X also can't equal 0. So when it comes to overall domain, guys, now this time we can only have positive numbers. No negative number. Only positive numbers. No 0 allowed because divided by 0. No negative numbers because you can't take negative, even root of negative numbers. Now let's do f over g of 16. And that's going to equal 6. I'll do this one. The 4th root of 16 cubed, which we saw as, I believe, 8 over 16 times 16. Now that's 8 over 256. I'd rather do 8 over 16 is 1/2, and 2 times 16 is 32. So this must be 1 over 32. I guess, yeah, we did 256 divided by 32, and we got 8, right? So I think that's going to work out, 1 over 32. Okay. Number 14 is the last one on the chapter test portion, and then we'll get to the cumulative assessment. It's a word problem. A football player jumps to catch a pass. How novelty. The maximum height h in feet of the player above the ground is given by the function h equals 1 over 64 s squared, where s is the initial speed in feet per second of the player. Find the inverse of the function, so that means solve for s. And let's just start with that. I'm going to multiply both sides by 64. And I'm going to take the square root of both sides. And you will get s equals... Now, the square root of 64 can be written as 8, so I'll get 8 root h like that. If it's initial speed, I guess we're just talking about the positive version, so there's the inverse. Use the inverse to find the initial speed of the player shown. Identify the functions are inverse functions. Now, I didn't notice this until just now. In the portrait, I guess the portrait matters, it shows 3 feet. I don't know if you can see that. It's right there. So it says the height of the player is 3 feet, so we have to find out what their initial feet per second velocity was. So h equals 3. So when h equals 3, we'll do s equals 8 times square root of 3. Now, we use the calculator for that one. 8 root 3, I'm getting about 13.856. We'll say 13.9. S is about 13.9 feet per second as an initial jump velocity. And then gravity takes hold and you only get 3 feet in the air when all is said and done with that. All right, guys, that is the chapter test portion. Let's see our time. Very good, 26 minutes. Now we're going to go ahead and get into the cumulative assessment portion. Again, if you want to find timestamps for each of any of the 1 through 10, go ahead and check it out down below, and we're going to have it. So let's go ahead and get started. This can hit anything from chapters 1 through 4. They tend to stress the current chapter that we're on, but we'll see. Like this first one is probably from this chapter. Identify 3 pairs of equivalent expressions. Assume all variables are positive. Justify your answer. Doesn't look like anything. Okay, A, it says assume all variables are positive. So these two will definitely match together. The nth root of a to the n is just a. Those cancel out, and it doesn't matter if these are even or odd roots. All variables are positive, so those are the same. Those are the same there. I don't see anything else that matches with that. That being said, it says 3 pairs. Okay, I thought it meant find 3 things that match. So that's a pair. This is a pair here, 1 over n and not that one, and the nth root of a. Those will be matches as well. So I'm going to kind of link them. Linky, linky. And then okay, well, this would be the a to the n over 2 power, and I don't see that one. This would be 1 over a to the nth root of a. This is a to the n. Nth root of, hold on, square root. Oh my gosh. Am I not seeing the last one? Okay, this one here would also be a to the n over 2. That one is just a to the n as is. This is 1 over the nth root of a, and okay, you know what, I want to explore that one more because I want to rationalize that one, and this is a to the n because I can't see anything else that goes with those. I want to take a look at 1 over the nth root, because okay, so this one here, I'm going to write this out. A to the negative 1 over n equals 1 over a to the 1 over n, which is 1 over the nth root of a. However, that's not rationalized. If I multiply this by, well, that would be tricky. I don't know if that helps me do anything by getting what I'm going to do here. If I multiply that by the nth root of a to the n minus 1 and the nth root of a to the n minus 1, that just gets me to a on the bottom, and on the top I have the nth root of a minus a to the n minus 1 power. I don't know what that's helping me get there. Oh, this one. Oh, wait a second. Why did I not see these as the same thing? What am I doing? Oh, you know what? Maybe I saw one as the n over 2 and I disregarded that as the other one. Okay, these are the same. These are the same right here. I don't know how I totally missed those ones, guys. So these are the same thing. Doesn't matter which order you have as long as that a is positive, or as long as all the variables are positive, you're good. So these ones don't seem to be the same in any which way. That one's nothing there. Just kind of ignore what's there. All the rest seem to be good. My justification is telling you that they're justified. Sorry for missing those two. Again, I probably looked at one and said, oh, that's a to the n over 2. And I looked at the other one that said, oh, that's a to the n over 2. And I thought I was looking at the same one twice. Total apologies. Okay, even though they were right next to each other. It's probably the first one I should have saw. All right, number 2. Let's get rid of this thing in green. Give me 1 second. All right, number 2. The graph represents the function f of x equals x minus some blank squared plus some blank. Choose the correct values to complete the function. Well, this is a parabola. It's got a vertex of -3, 2. So that's what we're going to stick in there. -3 for h, -3 for h, and 2 for y. Literally like that. Now, when it cleans up, I mean, that would be the answer. It's -3 and 2. When it cleans up, it actually looks like an x plus 3 inside of there. There's still the plus 2 like that. So I don't know which way you want to write it, but -3 is a number that goes in. 2 is a number that goes in. We use them in those specific spots. Probably not so much from this chapter and more from, I already forget what the other chapters were. Number 3, in rowing. I think it was the last chapter. In rowing, the boat speed s in meters per second can be modeled by s equals 4.62 times the 9th root of n, where n is the number of rowers. The more rowers you have, the faster you can go, but not by, there's diminishing returns, it looks like. Find the boat speed, part A. Find the boat speed for crews of 2 people, 4 people, and 8 people. Okay, so back to the calculator we go for this one. Let's go to our stuff. Let's clear these ones out, and let's look at y equals 4.62 times the 9th root of n. Now, if you want to do the 9th root of n, you could do x to the 1/9 power. Totally fine, totally fair. This time I'm going to go to my table. I'm going to ask for values this time, and I'm going to ask for 2 people, 4 people, 8 people, and these will give us speeds. All right, so for 2 people, we're looking at about 5.0 miles per hour. So 2 people. So about 5.0, is it miles per hour? Oh, meters per second. Meters per second. 4 people. Sorry that you can't see what I'm writing. You're just looking at the numbers for now. S is about 5.4 meters per second. And then 8 people, we have about 5.8. So S is about 5.8 meters per second. So you can clearly see they're diminishing returns. It's not like you double your speed as a result of it. I'm sure it helps a little bit. There's probably a fatigue thing going on as well that says you're exerting less energy as a whole, which would be nice. Does the boat speed double when the number of rowers doubles? Explain. So no, it does not. No, because look at the numbers. Because the function is not linear. Well, because the function is radical. Is a radical with a 9th root. So basically, there are diminishing returns. Basically, from 1 people to 2 people, I think it's a little more substantial. You go from 4.6 to 5. I mean, it increases sort of by 0.4 meters per second every time you double, it looks like. Find the time in minutes it takes each crew in part A to complete a 2,000 meter race. Okay, so this one asks you to explore some things when it comes to unit conversions, things like that as well. So find the time it takes each crew in part A. So part A has these numbers here. Now, I rounded them, but these are rates. At least keep that in mind. S is kind of like your R here. Distance equals rate times time, and we're going to find a time based on distance over rate. Now, our rate in this case will be our S value. I'll put it in green just to remind you that S is R in this case. Okay? Now, our D is 2,000. So 2,000 over S. Here, let me put R to begin with, then it turns into an S afterward. That's not a 5, by the way. That is such an S. It looks so S-like. I have no idea how anyone could ever confuse that for a 5. Okay, so 2,000 over 5. Darn it! S. We're going to do 2,000 divided by those numbers. This is where I actually would be better off not using the table that I had in the calculator, but going into what I did before. Let's do 2,000 divided by, and then let's do that thing here. Vars, y vars, use our function, and do the exact number for 2 people, 4 people, and 8 people. People. And this is the times they're going to take. These are in seconds. They want it in minutes eventually. So I'm going to write down these numbers here for 2, 4, and 8. Give me 1 second. I'm doing some stuff. I'm copying. You can take a look. I'm copying and pasting the original thing I had here. I'm going to erase that. I just want to write less. So time, the first time for 2 people is going to be longer than the others. It's going to be about 400.8 seconds. Now, these are not the final answers, just so you know. We got to divide these by 60, and I probably should have done that. Actually, let's go back. They said do it in minutes. I got to divide these times by 60, okay? So we're going to take this number divided by 60. This will be in minutes. We're going to take this number divided by 60. Hopefully you can clearly read what we're talking about. And this number divided by 60. So these are the times we want to look at here. 6.68, 6.19, and 5.73. I'm going to do a couple decimal places. That doesn't mean that many seconds, by the way. We're not converting that right now, unless they want us to convert that. So time is about 6.68 minutes. Time here is about 6.19 minutes. And time here is about 5.73 minutes. Cool problem. Cool problem, bro. Like the story of the rowboaters. It's cool, bro. All right. Totally. So, that's it. Number 4. A polynomial function fits the data in the table. What time is it? 36. Let's see if we can finish in the hour. Use finite differences to find the degree of the function and complete the table. Explain your reasoning. So I don't think we're actually coming up with a formula, but we are coming up with the degree. Well, you can do that. There are a couple things. Well, you know what? You might want to come up with the function for it, unless you can figure out how these things trickle up in terms of differences. It might take some time. Now, sometimes I screw up on these, so let's hope I don't here. Negative 26 minus 8 plus 4 plus 10 plus 10. From there, we got differences here are plus 18 plus 12 plus 6 plus 0. And it seems like this has the finite differences right here, which are minus 6, minus 6, minus 6. So 6 less than before. So you can trickle up if you'd like to, but it needs trickling up, which means we need to go from one bit to the other bit like this. And I don't know if I'm writing the things right. I'm trying to. I don't know, like that. Let's see. If I do another minus 6 here, then this would actually be a minus 6 there. And then this would be a minus 12. Yeah, I guess I need these. I guess I need one more minus 6. This would be a minus 6 and minus 12. And 10 minus 6 is 4 plus 4. 4 minus 12 is negative 8. So we got to do 18 plus 4 to get 22. And 22 minus 8. Really? 22 minus 8 to get, so it's a cube. Oh, by the way, this is a cubic. And 22 minus 8 to get 14. So I believe they should be 22 and 14. And then if that's the case for them, then you could also plug them into your calculator, into your cubic if you do that. So just for the sake of practice, because we didn't see this in the review, let's go to our stat edit and let's type in these numbers. Negative 4 for x. I'm using my table. I just totally screwed up there. Hold on. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Oh, hold on. We don't know 2 and 3 yet technically. So let me get rid of those ones. And then we have 28, 2, negative 6, negative 2, 8, and 18. Now from here, we know it's a cubic function, so we're going to clear this out. We're going to do stat and calc. Actually, let me do one more thing. I have to turn diagnostic on. I'd like to. So we can see that r squared was 1. Diagnostic on. Okay, stat, calc, cubic regression of that set. And here's our formula. Now that b is supposed to be 0. You can clearly tell 1.4 e to the times 10 to the negative 12th power. So our equation is actually f of x equals negative 1x cubed plus 0x squared plus 11x plus 8. So here's the equation that we have. Okay, if we substitute 2 into here and 3 into here, what do we get? f of 2 is negative 2 cubed plus 11 times 2 plus 8, which negative 8 plus 22 plus 8. Negative 8 plus 8 is 0, so you have 22, which is what we got there. And then f of 3 is negative 3 quantity cubed plus 11 times 3 plus 8, which is negative 27 plus 33 plus 8. Negative 27 plus 33 is 6. 6 plus 8 is 14, which is what we got up there. So two different ways to confirm it, either working trickling up from that or what we have there. Either way works with that given equation that we got. Okay, explain your reasoning. I did plenty of that. Number 5. A city charges $3.70 per 100 cubic feet of water used. And we have this tank here. Sorry, what is this, a pool? Oh, it's a pool. And I copy and paste the pool. Le pool. Le pool, le pool. All right. $3.70 per 100 cubic feet. All right, part A. What is the cost of filling the pool to a depth of 3 feet? So we need to find the volume of this pool up to 3 feet. You can ignore the 5. That's just how tall the pool is, but the pool water's only going up to 3. So our radius is 8 feet if the diameter is 6 feet. So your volume of what we're going to use is pi r squared, area of base, times height of 3. That's 64 pi times 3, which is 192 pi cubic feet. Let's leave exact for now as we do that. If we have $3.70 per 100 cubic feet, and we need to figure out the cost of X dollars per 192 for our 192 pi cubic feet, then we are going to multiply both sides by 192 pi with this. So X is going to equal 3.7 times 192 pi all over 100. And that'll give us money. So I'm going to go to the calculator and do that. 3.7 times 192 pi, all divided by now, 100, which is 22.317. So if we're talking about money, $22.32 about for the cost of what the city charges for that based off the amount of water used. Part B. There are about 7.48 gallons in 1 cubic foot of water. Express the cost of water in dollars per 100 gallons. Okay, I don't think that has to do with our depth of 3 feet. It just says per 100 gallons. So $3.70 per 100 cubic feet. We're multiplying 1 cubic foot of water by the conversion in gallons. 7.48 gallons. So we're going to do a per gallons bit. So 7.48. So that cost, it says per 100 gallons. So I have to multiply that by 100 after. I'll have to multiply top and bottom by 100, I think. So let's do times, let's see. So when this cancels out, oh, this is in gallons, by the way. So this is it for 7.48 gallons. Okay, so let's see this. We have 370 over 7.48 gallons. We need to figure out for 100 gallons. So that's our conversion there. So $3.70 per 7.48 gallons equals how much money per 100 gallons. Once again, we're going to multiply by 100 here, where X is 3.7 times 100 over 7.48. Yeah, we just had to multiply by 100 there. I just wasn't certain, but now I am. All right, so 3.7 times 100, which is 370. I should have known both times. Divided by 7.48. And that's 49.46. That's dollars per... Oh, it says per 1 cubic foot of water. Hold on a second. Then we already have the conversion. Hold on. Then I'll take that all back because this is already 100 right here. We already have 100 right there. So this is already good. So this is This is good right here. We just got to do the division there. I'm sorry. We'll just stick to that. So I think it's 0.49 then. So 3.7 divided by 100. Oh, this is 100 gallons, by the way. 100 gallons. 3.7 divided by 4, or 7.48. I was like, why would it be so expensive? All right, so around 49 cents per 100 gallons. Like that. Okay, part C. You add water to the 3-foot deep pool in part A until the water is 1 meter deep. The density of water is about 1,000 kilograms per cubic meter. What is the mass of the additional water? You add it to 3 feet until it's 1. Oh, it says 1 meter. Hold on. 1 meter is more than 3 feet. Okay. 1 meter is 3 point. I don't know the conversion. I know 1 meter is. Hold on a second. I know 1 meter is 39.37 inches. Now, that's not exact. That's approximated, but that's just what I hear online. So, do they expect us to know how much a meter is? And it says, what's the mass? It says 1,000 kilograms per cubic meter. Density is 1,000 kg per cubic meter. So we need to convert our feet to meters in order to work this thing out. Our radius is 8 feet, which there are 12 inches in 1 foot, and there are 39.37 inches in 1 meter. Which means when it comes to conversion bits, feet cancel, inches cancel there, and you're left with 8 times 12 divided by 39.37. 96 divided by 39.37. All right, clearly not a clean number, 2.43 something. I'm just going to put around 2.4. I have this number stored in my calculator right here. So I'm working meters off this thing to get the volume of the pool when you add just enough for it to go up that little bit more. Now, we don't care about the 3 feet that we already had. We just care about the additional that we're adding to it. So when we go from 3 feet to 1 meter, 3 feet is 36 inches. And 39.37 minus 36 equals 3.37 inches. When you multiply by when you multiply by 1, wait a second. When you divide by 39.37, when you divide by 39.37 inches per meter, you get that many meters. So 337, hold on, I need to store, give me 1 second. This is kind of a tricky problem because you got to do all this calculation stuff. What was this? Radius? I'm going to store this as R. Where's R on here? OP. Is that R? No, that's T. I can't see these letters. There's R. Store this as R. Sorry, my screen wasn't bright enough. So there's my radius number. I'm going to store this one as my height. This is 3.37 divided by 39.37. And this is going to store as my height. There's H. Okay. I don't know if you saw that my face brightened up when I brightened up my screen. All right, so we have H and R. We need to do, so that's around 0.09, whatever, but that's meters. So that's how many meters we're adding to this thing. So the volume that we're adding is area of base, pi times that many meters squared, times height. And again, I have exact answers in here that I'm going to use. So we're going to do pi times r squared. That's W. Give me 1 second. I can't see it anymore. I lowered my brightness. I have light sensitivity issues. I can't look at bright screens for too long. So I got to brighten it for a second longer. Is this H? That's pi, but I had to hit alpha. So pi r squared times height is going to be the volume of this pool. Hey, what happened? No. Let's do that again. Pi, sorry about this. R, this is just a vision thing for me. R squared times height. Okay. Now this is how many cubic meters the volume is that I'm adding to the pool. That's about 1.5989 cubic meters added. Now they said density was about 1,000 kilograms per cubic meter, and density is mass over volume. So we have 1,000 kilograms per cubic meter equals this unknown mass over 1.5989 cubic meters. So what we're going to do when we multiply both sides by 1.5989 is get our mass, and that'll be in kilograms, which is a decimal shift. That's 1,598.9. I'll put 90. 1599. I'll put 1599. About 1.1599 kilograms of mass. Maybe 1600 if we see 39.37 is rounded. I'm sure there are other numbers that trail it. Maybe this is supposed to be about 1600. Let's just do that because I don't know what we're supposed to get exactly. It seems pretty approximate to that, and I'm sure that it's more than just that exact bit. So about 1600 kilograms when all said and done. Let's just get around there. It looks good. All right, that's part C. Let's move forward. Number 6. Oh, we have 9 more minutes till we have the hour mark. I don't think I'm going to make it. I screwed up a lot typing the calculator there. Which equations are represented by the parabolas? Which equations are functions? Please place check marks in the appropriate spaces. Please check marks. Place check marks in the appropriate equations. Explain your reasoning. I'll explain verbally. All right, so if it's a quadratic, it's a parabola for a y equals x squared. So y equals x squared is a parabola, indeed also a function for that. X equals y squared will be a parabola, but it's a sideways one, so it will not be a function because sideways parabola biz. This is a square root function, so it's not a full parabola by any means, but it is a function. It passes the vertical line test. And this is the equation of a circle. It's neither a parabola nor a function for number 6. Okay. So if I were to give some explanation, this is the appearance of this graph. This is the appearance of this graph. This is the appearance of this graph. And this is the appearance of this graph. Those are my little bits to explain away how we can kind of determine what's functions, what's not functions, things like that. Like, what the function? What the function? Number 7. What is the solution of the inequality shown? Well, 2 root x plus 3 minus 1 is less than 3. We'll add 1 to both sides. The screen is too bright now. I brightened it too much. We'll add 1 to both sides. We'll divide both sides by 2. And we'll square both sides and subtract 3. So x is less than 1. Now, as far as domain goes here for the x plus 3 must be greater than or equal to 0 to begin with there. So x must be greater than or equal to negative 3. So as far as all that's applied there, x needs to be between negative 3 and 1, including negative 3, not including 1. That's the final. So we're looking at C. C is the answer to that one. All right, number 8. Maybe we can fit within the hour. Depends on how fast these questions go. Which function does the graph represent? Explain your reasoning. Oh, I can get that one. So it's an upwards facing graph, so I'm scratching out these two when it comes to vertical, the reflections, those reflect over. It's going to be C. D would have a horizontal translation. So, that one would move to the left side. These ones would flip over in some sort of way, so it can't be those ones there. It's going to be C. I don't know about the whole, this part with 2. I guess absolute value of 2 is 2. Up 2 over 1, that works out, and the negative 1 is 0, negative 1 graph. So 8's graph is C. Number 9. Your friend releases a weather balloon 50 feet from you. The balloon rises vertically. I might have to draw this. When the balloon is at height h, the distance between you and the balloon is given by that. So, okay, let's see. So here I am. Here's friend. This is supposed to be ground level. They released the weather balloon right there. Okay. It's 50 feet from me. No, they're 50 feet from me when they release it, I believe. 50 feet. The balloon is at height h. The distance is given by square root of 25. Okay, I agree because Pythagorean theorem, right triangle. Square root 2500 plus h squared. H and T are measured in feet. Find the inverse of the function. What is the height of the balloon when the distance between... Okay, I guess I didn't need to draw anything. But doing the drawing would have gotten me that portion by Pythagorean theorem. So D equals square root of 2500 plus H squared. I am going to square both sides. I'm going to subtract 2500. And I'm going to take the square root of both sides here. There's no plus or minus here. It's just the square root of D squared minus 2500. In both cases here, we're only looking at kind of positive results. So D squared, square root of D squared minus 2500. What is the height of the balloon when the distance between you and the balloon is 100 feet? So here's the inverse. And H now equals square root of 100 squared minus 2500. 100 squared is 10,000. So square root of 10,000 minus 2500 equals square root of 7,500. 7,500 RPM. Square root of 7,500 is about 86.6. 86.6. That is an 8. 6 feet in the air. Okay. All right, one more question, number 10, and about 4 minutes to go before the hour mark. Let's see how we do. The graphs of two functions f and g are shown. Let's do a whole new page just in case. Are g and f inverses? Explain your reasoning. This will be much quicker than 4 minutes. Based on not just the line, because you don't get the same tools that I do each time when it comes to these things, but based on this line y equals x, you can ask yourself, is that this is true symmetry on both sides? The answer is no. Now you can also, you can look at that and see for yourself, but as we explore this a little bit deeper, and I should really copy and paste this thing over, I'll stretch that out right to the hour mark. Just take any one value, and if you can disprove by counterexample that they don't get the same value out when swapping this thing, then that's just too dang bad. So for f, we have a point on this graph, for example, right here, that is 1, 3. Now g should therefore also have a point. Does g have a point that's 3, 1? Here's 3, here's 1. No, it's not there. The answer is no. So these are not inverses. It just takes 1 point to show that if the x's and y's don't swap, then they're not inverses. For this to be this exact inverse of f, you know, it's going to have to go this way. It's going to have to hit, whoopsie. It's going to have to go, let's see. I'm not very good at doing this right here. It's going to have to go this way. It's going to have to hit 3, 1 and kind of curve up and into there. It's going to have to curve out that side. What you see in black is more of the inverse of that one than what they have there. So that would be it. That's not it. So therefore, no, they're not inverses. For any xy from f, we don't get a yx match of g, basically, is the reasoning behind that. Now, there may be some false positives. Maybe right here they have the exact same x, y, y, x, and you flip them right there. And there could be ones even when they intersect right there and things like that. But if it's not always, it's not a guarantee. It's not an inverse. That'll be it. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. This concludes Chapter 4. Some little tricks here and there, and hopefully we addressed all of them that we needed to do. Thank you so much. Take care. I will see you in Chapter 5. Peace out.